Hello and welcome back to Introductory Electromancy. Today we will be learning about metal oxide semiconductor field effect transistors, or MOSFETs. Now, in the previous episode, we talked about JFETs, junction field effect transistors. However, there are a few loose ends I wanted to tie up. For one, I never drew the full schematic of what we were actually testing. It's not very complicated, but in the interest of completeness, I should note it. We have a 9-volt battery, acting as our power supply. Then we have our JFET, which is an N-channel JFET. So it gets a little arrow pointing this way. That lead, the gate, is what we were messing around with. Now in this specific circuit, it looks like I did the LED followed by the resistor. It doesn't actually matter which order you put the LED and the current limiting resistor. Because they are in series, they will necessarily have the same amount of current flowing through them. This is a 1 kilo ohm resistor, 1/4 watt. You could also write this as 250 milliwatts, depending on your preference, dear viewer. This is not my most beautiful schematic, but there we go. That is what we built and poked and prodded last time. Oftentimes you'll see schematics with a ground symbol added to indicate where we are defining to be 0 volts. In this case, it is the negative terminal of the 9-volt battery. And as you will recall, this is the lead we were playing with. In the interest of completeness, I should probably note the part number of our junction field effect transistor, MPF102. Now, the other loose end I wanted to tie up was regarding the oscilloscope. That oscilloscope, this one, right here. I said that I built it from a kit, but it is not entirely built from a kit. You can get a kit for most of the parts of the oscilloscope. I'll link it in the description. However, I added some parts. This kit is for a single tiny oscilloscope that fits on a breadboard, which is cool, but the input pins are quite sensitive, and I was worried that I was going to destroy it. So I took the time to put it in an enclosure and add some protection circuitry that it does not have by default. I drew the schematic on a piece of paper and stuck it to the side of the oscilloscope. See if I can make it visible to you, dear viewer. So, both of the signal lines have this protection circuit. It's a 56 kilo ohm resistor in series with it, and then a diode bridge, and this circuit, which turns on and short circuits the input once it exceeds somewhere between 5 and 12 volts. It has been years since I thought about this. Should I have tested it before I started recording this? Probably. But in any case, this is the schematic you would need to build if you wanted to duplicate my oscilloscope. Since it runs on 5 volts, I used 4 AA-sized nickel metal hydride batteries as its internal power source. And then each channel has a copy of this circuit, which is a 56 kilo ohm resistor, a shunt regulator, we will call it, that makes sure that the voltage does not exceed the input limit, and then a switch if you want to divide the input voltage by 20, which is useful if you want to measure high voltages, and a switch that either puts a capacitor in series with the input for AC mode or shorts it out and directly connects the input for DC mode. And a lovely warning. But if you want one of these, dear viewer, you can copy my schematic and use parts. Use this kit of parts. If you are not yet comfortable soldering surface mount parts, then you can buy it as a pre-assembled module, naturally for more money. Looks like a whole extra $15. Now, if you want to become comfortable with soldering surface mount parts, then there is a convenient beginner's guide to surface mount device soldering, which I will link in the description. Now, that said, it is time to introduce our next component, the MOSFET, the metal oxide semiconductor field effect transistor. Because if there's one thing you need in your life, it's more acronyms. Now, I have simply wired our test MOSFET circuit in parallel with our existing JFET test circuit. And it's important to note that I could just keep adding new circuits in parallel and running them all off of this same 9-volt battery up until the current output limit of the battery itself. Your house, for example, has many outlets, and hopefully all of them work if you plug something in. And for the purposes of this discussion, let us assume they are all identical. They are all wired in parallel. You can unplug and plug things in, and they all still get the same voltage. I will be going into more detail about series and parallel circuits later, but to touch on it, a series circuit is when you have two components that are strung end to end like this. Someday I'll get an actual pad cam. Today is not that day, dear viewer. Series as opposed to parallel where the two circuit elements are side by side. And then what is the net effect of these two circuit configurations? Well, in a series circuit, all the components have the same current. That is because the current has to flow through both of the components. It will necessarily be the same value. However, the voltage is going to be divided between the two components. In a parallel circuit, the voltage is the same across both components, but the current is what is divided between them. This concludes our very, very brief introduction of series and parallel circuits. Now for some practical poking and prodding. PPP, practical poking and prodding. In the last episode, I went into a whole description of why our JFET circuit acts the way it does. Interesting. I like how I'm getting some sort of intermittent failure here. So this lead acts as an antenna. In the previous episode, I attributed this effect to power line hum, but now that I have thought about it more, some of it may also be due to the radio frequency electromagnetic fields surrounding me. Because I made a very similar setup with this MOSFET, which will act somewhat similarly to this junction field effect transistor, and it behaves much more stably. That is, the MOSFET does. So I have made it so that the gate lead of the MOSFET is accessible here, and you should not do this if you want a reliable long-term circuit for reasons that I will get into shortly, but you can touch the positive terminal and then the gate to turn it on, and touch the negative terminal and then the gate to turn it off. This is what I had expected the JFET circuit to act like, instead of being all squirrely. It's kind of funny that the very first circuit demonstration I gave you, dear viewer, is showing complicated, unexpected effects, but it is fitting. In any case, I think that the JFET is also responding to radio frequency input because it has such a low input capacitance. As you will recall, capacitors tend to smooth out changes in voltage over time, and I took the time to look up the actual input capacitance of the MPF 102, and it is 7 picofarads. The MOSFET I'm using here, BUZ11A, has an input capacitance of 1,400 picofarads. So the additional input capacitance is swamping out whatever strange electromagnetic noise spikes are making the JFET so sensitive. The flip side of this means that the JFET would be an excellent first stage for a radio receiver, but the BUZ11A MOSFET would not. Now, so we have our MOSFET. We can see we give it a resistor, an LED, and then depending on whether we connect the gate to the positive terminal, which turns on the LED, or to the negative terminal, which turns it off, through my hand, which will function as a couple mega ohm resistor, about 4, give or take, dear viewer. This MOSFET is a type of voltage-controlled switch. MOSFETs are the most common type of transistor, at least in terms of raw number, that have been manufactured, because these are the basis of computer chips. Of course, computer chips use much smaller ones. This MOSFET is intended for power applications, where it will be switching a larger current, as opposed to a digital logic application, where it switches a very, very tiny current. Yeah. All right, so great. It's a thing. We switch it with voltage. Let me draw the schematic of what we have built here. Are we not having fun yet, dear viewer? Are we not? Are you not entertained? So, this thing, the way I wired it, has a 9-volt battery, very happy little 9-volt battery with a positive terminal. That positive terminal then goes to a 1 kilo ohm resistor, then an LED. A 1 kilo ohm quarter watt resistor, or 250 milliwatts if you prefer. Now this LED is green. And then our active part is, and bear with me here, an N-channel enhancement mode metal oxide semiconductor field effect transistor, which is kind of a mouthful to say. What does enhancement mode mean? We will get into it, dear viewer. Oh boy, will we ever. Then I'm going to add a ground symbol to indicate where ground in this circuit is. And this is too tiny for you to see. I'm sure I'll get into a better flow with these things as time goes on. But here we have our schematic. This is the gate connection of the MOSFET. We'll give it a nice little G to indicate that. This is the drain, this is the source. Now, that represents this little chunk of circuitry here. It also includes the battery that would be connected to those clip leads if we wanted these lights to turn on and off the way that, well, you know, everyone loves blinking lights. But how does the MOSFET work? Now, you will recall I started you off by explaining the JFET, which has a PN junction but with two leads in either the N or the P type, depending on which is the larger one. Current can flow from this lead to this lead normally, but if you reverse bias this PN junction, it forms a depletion region which has no mobile charge carriers and expands, cutting off the channel. So by varying the size of this depletion region, which is controlled by how big this voltage is, you can control how much current flows through the device. Now, the MOSFET is very similar in construction. Your friend, the MOSFET. I'm going to begin by describing a depletion mode MOSFET, which is the most similar to a JFET. You would have some thin slice of N-type semiconductor. You would have some sort of insulating gate material, usually silicon dioxide, but this is to be an insulator there, and then you will have another terminal called the gate, which is electrically insulated from the semiconductor. As before, current could flow through here if there is no external voltage applied to the gate, because N-type semiconductor is conductive by nature of its free electrons. But if you apply a negative voltage to the gate, like so, then the extra negative charges here that you have induced at the gate terminal tend to repel these electrons away, creating a depletion region or depletion zone, which can be controlled in size depending on the amount of voltage applied. So the N channel depletion mode. MOSFET pictured here functions more or less identically to the JFET with the addition of an oxide layer and a conductive gate. This structure is where the name of the MOSFET comes from. Because there is metal, then oxide, then semiconductor. And it is a field effect transistor because it is this electric field's effect that is causing the change in how wide this channel that is conductive is. You could also build this with p-type silicon. It would function identically, except applying a positive voltage to the gate would tend to cut off current flow. However, most MOSFETs in use are enhancement mode MOSFETs. Enhance. And I'm going to use the example of an N-channel. Enhancement mode MOSFET. Now, the N-channel enhancement mode MOSFET has an interesting structure. You actually have two little areas of N-type silicon and then a larger area of P-type silicon. Then you have your gate oxide, which is non-conductive. And then your metal gate. It's worth noting that currently these gates are not actually usually made with metal. They're usually polycrystalline silicon. Regardless, it's still called a MOSFET. So, because this has an N, then P, then N structure, there will be a reverse bias diode in here somewhere, no matter how you try to apply a voltage to these two leads. So the device will not conduct. But if you apply a positive voltage to the gate, then something interesting happens. So the positive voltage here repels the extra holes in the p-type silicon, pushing them away from a thin region here. Now, this by itself would just make this region even less conductive. However, you will recall from the very beginning of this that N-type silicon is not entirely possessing electrons as its free charge carrier. There will be trace quantities of holes in N-type silicon, and there will be trace quantities of electrons in P-type silicon. This is because in the matrix of atoms, some of them will jostle enough to shake loose an electron, which leaves a hole in its wake, creating mobile electron-hole pairs. So P-type silicon, its majority carrier is holes. N-type silicon, its majority carrier is electrons, but there will be trace amounts of the other type of charge carrier present in each of these types of silicon. So why does this matter? Because those trace little electrons, which are present in small quantities in the p-type silicon, those are attracted to the positive charge here. And so it has the effect of creating a thin layer that effectively turns into N-type silicon. So-called carrier inversion. This diagram is getting rather busy. But this layer between these two N-type doped regions under the gate has its spare holes repelled away and any trace electrons attracted to it, creating a conductive N-type region, which allows current to flow. And you can make this in reverse, called a P-channel enhancement mode MOSFET, where you apply a negative voltage and it converts the area under the base from N to P-type semiconductor temporarily based on the amount of charge that is stored at the gate here. This thing has this lovely schematic symbol. The broken line indicates that it is enhancement mode. It is a solid line for depletion mode. This connection here indicates that the substrate is connected to the source terminal. Source, drain, gate. I know these are the diagrams you come here for. The upshot is if you apply a positive voltage, you convert a thin layer of this P-type semiconductor effectively into N-type semiconductor, creating a conductive channel between these two N-doped regions. And you can see this in our practical example. Now, there are a lot of equations describing these transistors which I have not touched on, dear viewer. This is because I am trying to give a whirlwind tour introducing you to the basic electronic components before I start explaining how you use math in order to calculate the desired operation of your circuit, because you kind of have to know what the parts are and what they do before you get into too much detail with each of them. Otherwise, this would be very boring. Now, the reason you shouldn't use this circuit for a practical application where you'll be relying on it is because of electrostatic discharge. This gate oxide layer here in a MOSFET is very thin. It is on the order of 10 nanometers thick. This means that the static charge that you, dear viewer, can accumulate, if this is grounded and you touch the circuit here, the static charge will just arc through the gate layer, permanently destroying the MOSFET by burning a little conductive channel through here. That is why so many components are marked as electrostatic discharge sensitive. It's because you act like a roughly 100 picofarad capacitor charged to between 2 and 8,000 volts. How much voltage can this gate layer in this particular transistor withstand? Well, it'll be listed under absolute maximum ratings. Gate source voltage plus or minus 20 volts. So you will note that 8,000 is a much larger number than 20. It's kind of impressive how much voltage you build up with static electricity. The reason it doesn't kill you when you get a static shock is because the current is very low. It takes about 30 milliamps to stop your diaphragm from working so you can't breathe, and about 70 milliamps to stop your heart, for those wondering. But the actual voltages involved in static shocks are huge. It takes about 1,000 volts to break down a millimeter of air. So if you can get a 4 millimeter long spark off of yourself, that means you have a charge of about 4,000 volts. That number is very approximate and depends on air pressure, humidity, and a variety of other factors. In any case, this has been your introduction to your friend, the N-channel enhancement mode metal oxide semiconductor field effect transistor. Everybody's favorite part. Don't build this circuit in real life because you'll destroy it with static electricity. For a quick demo, it's probably okay. That's all for now.